When you first open up the signal in the TF32 software, you see the stereo waveform on the top and the spectrogram on the bottom. The first thing to do is to turn off the waveform display by right-clicking on the waveform, selecting Wave Plot, and then uncheck the box that reads Show Waveform Plots. Next, to view the spectrum corresponding to the point where we place our cursor, select the View menu at the top, select Open, and then select Spec. Now we want to scale the spectrogram. Right-click on the spectrogram and decrease the viewable frequency range to a value that reasonably accommodates the signal frequencies. Next, for ease of viewing, I recommend that you decrease the viewable dynamic range to 32 and decrease the floor to -48 dB. These are the lower limits of the software settings. This is where the fun begins. You can see that as we move our cursor from left to right, the spectrum of the signal changes. If we select LP on the right, we get a smooth representation according to a linear predictive analysis. H is selected by default, which shows the unsmooth spectrum. I've noticed that the linear predictive analysis tends to merge two peaks when they're close together in the low frequencies. So in this case, you can use the spectrogram as your guide as to whether to use smoothing or not. In the low frequencies, there's just a single peak indicating that no lowering is taking place. Then around 1500 Hz, we see two distinct peaks. The higher peak corresponds to the input, and the lower peak corresponds to the output. We see that frequency lowering continues until we get to an input frequency of around 6100 Hz, at which point the information is lowered to around 2100 Hz. Finally, the other thing I like about this program is that we can easily scroll from one file to the next while maintaining our program settings by simply selecting the previous or next buttons here at the top. Here you can see the same signals before, but this time I only saved the recorded output signal. Now I'm going to scroll through some other examples for you. Here we have the same device with a slightly higher start frequency. And here again at a slightly higher start frequency yet. Here we can see frequency lowering for a device with frequency transposition. And again, for this device we only saved the recorded output signal. First thing we're going to do is decrease the viewable range so that we can accommodate the signal frequencies. And we see that the frequency lowering starts at about 1000 Hz, and I'm going to select H so we have a better representation of the peaks. And here we can see three distinct peaks. The lower one referring to the lowered information. The middle one here corresponds to the original input signal. And here we see up here a little bit of distortion. Here we have frequency transposition starting at 6 kHz. And for this signal we have frequency transposition starting at 1000 Hertz as before, but within an expanded mode in which we have an additional set of high frequencies that are being brought down with this extra peak here. There's the original input signal. Here's frequency lowering, frequency transposition in the basic mode, and frequency transposition in the expanded mode. Finally, one last setting with frequency transposition in an expanded mode. Here's the original input signal, frequency transposition in the basic mode, and frequency transposition in the expanded mode. We see multiple peaks in the output originating from a single peak in the input, the original signal, frequency lowering in the basic mode, and a little bit of distortion. Observe the smooth spectrum.